Let's take a look at Chapter 4. And our first section is Section 4.1, Inverse Functions. And the first topic is to identify one-to-one functions. And we have a definition of one-to-one function. It says, for every x, there is only one y, and for every y, there is only one x. That's a hard definition to work with, so we've got an easier definition. Our easier definition says, if you have any of the following, it is not a one-to-one function. If we got x to an even power, y to an even power, it's not a one-to-one function. If you got the absolute value of x or the absolute value of y, it's not a one-to-one function. If you have the plus or minus symbol, or if you have x equals a number or y is equal to a number. Unless, actually, let me put those as powers. Unless there is a condition put on x. For example, if you have y is equal to x squared, that right there would not be a one-to-one function. But if we put where x is greater than 0, for example, by putting a condition on there, we're making it so it is one-to-one. Now, it's possible you might have a condition on a function that would not make it one-to-one, but typically that's the purpose of putting that condition on there. Excuse me. Okay. So identify one-to-one functions. Get my tablet going here. If the question was whether these are one-to-one functions, we got y is equal to x squared minus 2. The fact we have an even power means no, this is not a one-to-one function. If we got y is equal to x to the third minus 3. Here, this would be a one-to-one function because we don't have an even power, don't have the absolute value of anything, don't have the plus or minus. Now there's a test called the horizontal line test. And this says if any horizontal line intersects the graph at 2 or more places, then it is not one-to-one. Might still be a function, but it's not one-to-one. So if I have this graph here, I see I can draw a horizontal line right here, and it intersects at 2 or more places. So the answer here is no, it would not be a one-to-one function. Now, our vertical line test still tells whether it's a function or not. This just tells the one-to-one portion. If I had this graph here, if I drew a horizontal line, intersects one place, draw one here, one place, draw one here, one place. No matter where I draw a horizontal line, the most it will ever intersect is one place. This would be a one-to-one, and it's also a function. Clear those off. Now, our second topic is to determine whether two functions are inverses. So let's look at that. Inverse functions. F and G are functions and are inverses if the following is true. If the composition of F and G is equal to X, and the composition of G and F is equal to X. So if that's true, that means they're inverse functions. For example, if I have f of x is equal to x plus 3, and g of x is equal to x minus 3. And the question is whether they're inverses of each other or not. Well, if I find my composition of f and g, that's equal to f of g. So we're going to take our f of x, which is x plus 3, and where our x was, we put in a set of parentheses. Now whatever's inside the parentheses right here is automatically what we'll put in here. So put g in there. But g is equal to x minus 3. And then negative 3 plus 3 cancels and we get x. And that's our first part. Our composition of f and g has to equal x. Then we do our second one. We find the composition of g and f, which is g of f. So we're going to take our g of x, which is x minus 3, and where our x is, we'll put in a set of parentheses. Now what's inside your parentheses right here is automatically what you put in here. So put f in there. But f is equal to x plus 3. So replace that with x plus 3. And 3 minus 3 cancels, we got x. Since we got x on both of these, the answer on this would be yes, they are inverses of each other. If one of them equaled something else, equaled x minus 7, for example, would not be there would not be inverses. Let me get a drink here. Now our third topic here is to find the inverse of a function. So finding the inverse of a function. Step 1. Replace f of x with y. Step 2. Interchange x and y. Step 3. Solve for y. And step 4. Replace y with our inverse notation. And then step 5, if necessary, use the graph to figure out how to make the inverse function one-to-one. For example, if I got f of x is equal to 7x plus 2, and I want to find the inverse. Step 1, replace f of x with y. So we got y is equal to 7x plus 2. Step 2, interchange x and y. Swap them. So where your y is, you put an x, and where your x is, you put a y. So we got x equal to 7y plus 2. Step 3, we want to solve for y. So I take the 2 over. We got x minus 2 is equal to 7y. Divide both sides by 7. So we got x minus 2 over 7 is equal to 7y over 7. So x minus 2 over 7 is equal to y. Or you could split this into two separate fractions if you wanted it in slope-intercept form. And then step 4 is replace our y with our inverse notation. So the inverse of f is going to equal to x minus 2 over 7, or 1/2 x minus 2/7 if you split it up into two separate fractions. One more of those. Got f of x is equal to x to the third minus 2. Step 1. Replace f of x with y. So we got y is equal to x to the third minus 2. Step 2. Interchange x and y. So we got x is equal to y to the third minus 2. Step 3 is solve for y. So I take negative 2, bring it over. So we got x plus 2 is equal to y to the third. Now that third power we can rewrite as 3 over 1. And we can raise both sides to a power equal to the reciprocal. So this is 3 over 1. Reciprocal, that would be 1/3. So we'll take both sides of the 1/3 power. I'm going to do that. These 3's cancel. The 1's are trivial, but they'll cancel also. And we got y is equal to, and putting this back in the radical form, this would be the cube root of x plus 2 to the first power. Whatever number's on the bottom here, that your denominator, that's what goes in your slot, that's your index. Whatever power is up on top is what goes inside. And then step 4, replace y with your inverse notations. We have the inverse of f is equal to the cube root of x plus 2. And that would be our answer. Now, exponential functions. We're going to take a look at a little bit of graphing on these. We won't spend a whole lot of time in this section. Now, if I'm trying to evaluate e to the third power, e is a number like pi. It's 2.7, a bunch of decimal places. So bring up my calculator. Okay. Now, if you're in graph mode, exit out, do a second mode. We want to do e to the third. So I'm going to do my second ln to do the e, and then to the third power, and then press enter. And that gives us 20.09, round to get two decimal places. Now, exponential functions. That's something like this. Y equals f of x equals 3 to the x minus 2 power. Now, what makes this an exponential function is it's got a variable in the exponent. Now, if you got more than a single variable up here, a single number in the exponent, you had to put parentheses around it. So when I plug this in the calculator, I'll make sure I put parentheses around the x minus 2. So to graph that, assuming that's the instructions, I go to y equals clear 3 caret, and then beginning parentheses, x minus 2, and closing parentheses. Those of you that have the newer TI-84, when you do the caret, it puts it up there in what looks like a little exponent box. After you do the x minus 2, you have to do a right arrow key to get out of the exponent. You do not need the parentheses around it. Now, if you don't do the right arrow to get it out of the exponent, it will not work on other problems. It'll work just fine on this one. But other ones, if you have anything more following this, it'll put everything up in the exponent. And then I'll push my graph. And that would be our answer. Now, they never just stop. It keeps going forever, skimming the x-axis, getting really close to it, but never touching it, never crossing it. It's actually an asymptote. Asymptote is an invisible line your graph skims at some point. Now let's look at one more. y is equal e to the x plus 5. Let's say we want to graph it. So go to my y equals, clear. I do the e, so I do second ln, and that puts e, puts a caret beginning parentheses, x plus 5, and then I'll press my graph. And this will look like this right here, more or less. Got a little bit too close there, but you get the idea. Now that's these first two. I got the applications here in compound interest, but that's covered in a lot more detail down in section 4.6. And so I won't cover that here. And actually 4.6 I'll let you watch the video, since it is so lengthy and I wouldn't be able to give it a accurate coverage here. Let's take a look at log functions. Now the first topic is to convert between log and exponential form. Now our log form looks like this. We got log, got a little b here that's smaller, it's set down. Q is equal to p. All of these might have names, but the only one that has a name that matters, that we use a lot, is the b. That's referred to as a base. Now our exponential form is b to the p is equal to q. What these forms allow you to do is if you have something in log form, you can rewrite an exponential. If you have something in exponential, you can rewrite it in log form. Example. If you got log base 2 of x is equal to 3, well, first thing you want to do is identify your b, p, and q. b is whatever number follows your log, that's smaller is set down. And then what follows that is your q, whatever might be there. And then the other side of the equals is always your p. So our exponential form is b to the p is equal to q. So we just plug in what we identified. b was 2, p is 3, and q is x. So that'd be our answer. Now on the other hand, if we have something in exponential form and you want to rewrite it in log form, well, same idea. We want to identify our b, p, and q. Your power is always your p. What's to the left of that is going to be your b, your base. And then what's on the other side of the equals will be your q. Now our log form is log base b of q is equal to p. So after we identified b, p, and q, we just plug it in. So we're going to have log base 5 of q. What was q? Q is x is equal to p, which would be 2. So that'd be our answer. Now sometimes you have to rewrite it. Like if I had square root, oh wait a minute, the square root of 5 is equal to 7. And the instructions were to write it in log form. Well, we can rewrite the square root of 5 as 5 to the 1/2. It's equal to 7. By the way, that doesn't equal 7, but let's pretend it does. And then you identify your b, p, and q. Again, your power is always your p. What's left of it is always your b, and the other side is always your q. So then our log form, log base b of q is equal to p. We plug in everything we identified. b is 5, q is 7, and p is 1/2. So that'd be our answer. Now I'm going to erase some of those. Now we have some special bases. If you just simply have log with no base, there's no number following that, then by default your base is 10. This is referred to as a common log. If you have natural log, it says ln, and there's no number here, your base is going to be e. That's referred to as a natural log. So, if you had a problem, that was natural log of 3 is equal to x, and your instructions were to put that in exponential form. You start to identify your b, p, and q. Now, since this says ln, our b is going to be equal to e. And then what follows that is our q, and then the other side of the equals is our p. And our exponential form is b to the p is equal to q. So we got e to the x power is equal to 3. And that would be our exponential form. If you had something in exponential form, you want to rewrite it in log form, well, same idea. It matches this exponential form here, so we're going to identify our b, p, and q. Our power is going to be our p. What's left of it is our b, and the other side is our q. And our log form says we're going to have log base b of q is equal to p. So we plug in everything we identified. B we said was e, q we said was x, and p we said was 3. Now when you got a base of e, it's always written as natural log. So that's ln x is equal to 3. And that'd be your answer. Erase all those. And that's converting between log and exponential forms. Now evaluating log expressions. Now, actually that goes hand in hand with the next one, apply basic properties of logs. It's best to show this by an example and then write down the property. Let's say we had log base 2 of 8. And want to evaluate this without using the calculator. Now our base is 2. Our goal on these, when you have a number, is you try to rewrite this number that follows the log, the 8, you try to rewrite that as a base to a power. Well, 8 I can rewrite as 2 to the 3rd. Now if these two numbers match, then the log and those two numbers are going to cancel, and the 3 drops out of the exponent, and that's our answer. Consider if I had this one here, log base 5 of 25. Well, 25 I rewrite as 5 squared. And again, if these two numbers match, then those in the log are going to cancel, and the 2 drops out of the exponent. Now sometimes it's kind of a challenge to get it in the right form to apply this property. For example, if I have log base 2 of 1 over 16, I want to rewrite 1 over 16 as 2 to a power, but maybe I can't see what it is directly. So I have to first, 16 is 2 to the 4th. And then, remember, if you have something in your denominator, you can move it up on top and the sign of the exponent changes. So this becomes log base 2 of 2 to the negative 4. And then if those two numbers match, log and those two numbers cancel, and the negative 4 will drop out of the exponent, and that's our answer. Now the property for that says we got log base b of b to the p power, that's going to equal to p. Now there's one more property I want to refer to. If you have 3 to the power of log base 3 of x minus 7, for example. If these 3's match, then those 3's in log are going to cancel, just like these up here. And the x minus 7 will drop out of the exponent, and that's our answer. Now the property for that, if you're big into properties, says we got b to the power of log base b of q is going to equal to Q. Let me grab a drink here. Okay, let me clear that off. Now, so another property of logs that we're going to use in combination with graphing. So let's talk about those. If I want to graph, for example, y is equal to natural log of x plus 1. Not too bad. Come over here, do y equals, clear. Here's an ln button, that's my natural log, and then x plus 1. And then press graph. Although it will never give us a correct graph, which is kind of a bad thing right there, but looks like that right there, but it never is that way. It keeps going forever. Calculator will have it just stop, but just keep that in mind. It keeps going forever. I won't graph this one. But let's say I had y is equal to log x. Still not an issue. I got a log button. Now this ln button here is base e, and this log button, you see right here, this is base 10. So we're covered. But the problem is when you have something that's another base, like base 3. What we have to use before we can plug it in our calculator is something called the change of base. And that means we're going to rewrite this as log of something over log of something. And I'll put the x minus 2 up on top, and I'll put the 3 down below. The way it always works is whatever follows your log goes up on top, and whatever your base is always goes in the bottom. Now you might look at this and say, well, that don't look any easier. It looks harder. Well, yeah, but it's no longer base 3. It's now base 10. And we have a log button. So in this one, I'm going to my y equals, clear, push my log, and then x minus 2. I'll put a closing parentheses on that, and then divided by log 3. And then press graph. And our graph for that would look like this right here. Again, it never just stops, keeps going down forever. That change of base also comes in handy if you're evaluating. Like if I had log base 7 of 8. I don't have a base 7 button, so I'll rewrite this. Now, change of base says you can rewrite it as any base. I could rewrite it as natural log of 8 over natural log of 7. Again, whatever follows your log goes up on top. Whatever your base is goes down below. The only two bases that make sense for purposes of this class are the log button and the ln. Now I'm going to do a second mode to exit out. The reason why the ln and log buttons make sense, or the options make sense, is because we've got buttons for those. So I'll push my ln button, 8, closing parentheses, divided by ln of 7, and press enter. Now give us 1.0686, rounded to 4 decimal places. Okay, let me clear that off. And we're to section 4.4, properties of logs. Now we got 3 main properties of logs. First one says log of something plus log of something. Addition becomes multiplication. Second one is log of something minus log of something. Subtraction becomes division. And if you got a number and then a log, it doesn't have to be a number, but typically it's a number that's in front of your log, then you can take it and put it as your power. First one is called a product property, second one is called a quotient property, and the last one is called a power property, if you dig into names. And what we do with these is you may start off with separate logs. Like this. And your goal is to merge them into a single log. Well, the only way we can use properties 1 and 2 if we're going that direction is if there's no numbers in front of the logs. Now notice that says log and these say ln. It applies no matter what your base is. So we said we can't have any numbers in front of the logs. But our third property says we can take a number that's in front of a log and put it as our power. So I can rewrite this as natural log of x to the third plus natural log of y squared minus natural log of z to the 7th. Now at that point we'll handle it from left to right. So I look at these first two logs, and we got log of something plus log of something. Well, that's property 1. Addition becomes multiplication. So this is natural log of x to the third y squared minus natural log of z to the 7th. Now we have log of something minus log of something. And subtraction from property 2 becomes division. So this becomes natural log of x to the third y squared over z to the 7th. And that would be our answer. Just shut my window. You think I live right next to the train yard, the way it sounds sometimes. Now we can go the other direction. If we have log of x squared square root of y over z to the third. Let me put a w down there too. W squared. You always have to look for the main thing that's happening. And the main thing that's happening is division. When I say main thing, I'm talking about I would use every element in the problem besides the log. Division would use the x squared, the square root of y, and it'd use the bottom part, the z to the third w squared. Well, division becomes subtraction. So this will become log of x squared. I'm going to rewrite the square root of y to the 1/2. Nowhere in this chapter do we want square roots, or radical symbols, I should say. Minus log z to the third w squared. Now we're looking for the main thing that's happening here. We got second power, the 1/2 power, multiplication. Now you might say, well, is the 1/2 power the main thing's happening? No. Only if you could answer this question, yes. Is everything being raised the 1/2 power? And no, it isn't. Only the y is. But multiplication would use everything. This times this. And multiplication becomes addition. So this is log x squared plus log y to the 1/2 minus, I'm going to put a parentheses here, because this minus has to affect everything that follows it. And here we got multiplication, z to the third times w squared. So multiplication becomes addition. So this is log z to the third plus log w squared. Now these have powers, and I put the power in front of the log, so it becomes 2 log x plus 1/2 log y. Remember, this minus is going to flip the sign of everything that follows it. So I got minus, I'll take this power and put it on front, minus 3 log z minus 2 log w. And that would be our answer. Grab a drink here. Clear this off. And we already applied change of base. So let's go on to section 4.5. Exponential equations. First one we'll take a look at is the equality of exponents. And this says if b to the p is equal to b to the q, then p is equal to q. And these should be powers. There we go. Very simple idea. Sometimes it's not so simple getting it in the right form. For example, if we have 2 to the x is equal to 8, and I want to solve this using the equality of exponents, what we'll do is we start with a larger number and we try to rewrite it as the other number to a power. Well, 2 to the third gives us 8. Now, equality of exponents says if you can rewrite both of these as 2 to a power, then the 2 is going to cancel, and you set the exponents equal to each other. So we got x is equal to 3. On the other hand, you could have a problem that looks like this. 8 to the x equals 16. If I start with my larger number, there's no way I can rewrite 16 as 8 to a power. 8 to the first is 8, 8 squared is 64. This time I have to focus on both sides. So I have to rewrite the 8 as 2 to the third, and I have to rewrite 16 as 2 to the fourth. Now notice this already had an exponent up there, so when I put my new exponent, I multiply them together, 3 times x. Now since they're both 2 to a power, the 2's will cancel, and we got 3x equal to 4. And then you solve for x, divide both sides by 3, and you get x equals 4/3. Then again, you just have to not do that one. There we go. On some of these, you just have to play with them to get them in the right form. Like that here, I got 27. I could rewrite that as 3 to the third. And I can rewrite that as 1 over 3 to the 3/2 power. Because whatever powers right here, that goes up on top, the numerator. And whatever number's right here, our index, that goes on the bottom. And if you don't have a number, it's by default 2. Well, that looks real close, but it's trapped in the denominator, so I can take that and move it up on top. So it becomes 3 to the negative 3/2. Remember, when you move anything opposite of where it's at in a fraction, the sign of the exponent changes. Now, since they're both 3 to a power, I can cross the 3's out and set the exponents equal to each other. And that would be our answer. Very simple idea, but as you can see from this example, not so simple to always get in the right form. That's a little bit tricky. Now there's some problems that you cannot work with equality of exponents. Consider this exponential equation. Exponential equation is where you got a variable in the exponent. 3 to the x is equal to 5. There's no way I can take the 5 and rewrite it as 3 to a power. I can't focus on both sides and rewrite them as the same number to a power. Excuse me. So solving exponential equations. Step 1. Get the part with the variable in the exponent by itself on one side. Step 2, take ln, natural log of both sides. Step 3, use properties properties of logs to get the variable out of the exponent. And step 4, solve for x. Okay, so step 1. get the part of the variable and the exponent by itself on one side. This is the part of the variable and the exponent, and it's by itself. There's nothing in front of it, there's nothing after it. We just got 3 to a power. So we'll go to step 2, take natural log of both sides. So we got natural log of 3 to the x is equal to natural log of 5. Step 3, use property of logs to get a variable out of the exponent. Well, we're going to take the x, put it out in front. Feel a sneeze coming on. Now then solve for x. Well, natural log of 3 is just a number. So to get the x by itself, we would divide both sides by natural log of 3. So then we're going to get x is equal to natural log of 5 over natural log of 3. Now the ln's cannot cancel there, though most you could do is you could plug this into your calculator and get an approximation. Now I'm not going to work it, but let me show you an example where you have a number over there, like this. To do step 1, we need to get the part with the variable and exponent by itself on one side. So you always do the opposite operation, so you can add 1 to both sides. Then we get 7 to the x is equal to 9. And now this is by itself on the left side. Nothing from it, nothing after it. We just have 7 to the power. And then you would continue on. Now let me show an e, because those are different. They're actually easier. Step 1, get the part of the variable and exponent by itself on one side. This is by itself. There's nothing in front of it, nothing after. We just simply have e to a power. Step 2, take natural log of both sides. So we've got natural log of e to the x minus 1 is equal to natural log of 2. Now step 3, use properties of logs to get the variable out of the exponent. This one works out nice because natural log and e cancel each other away. Always. And that gives us x minus 1. And then solve for x. I'll take the negative 1, move it over. We got x equal to 1 plus natural log of 2. And that would be our answer. Let me grab a drink here. Now let's look at log equations. So solving log equations. Step 1. Get everything with a log on one side, numbers or constant terms on the other side. Step 2, use properties of logs to get a single log. Step 3, you might be able to use basic algebra on step 2 also. Step 3, use the definition of a log to rewrite in exponent form. This is a b to the p power is equal q definition. Step 4, solve for x. And then step 5 is to semi-check your answer. You don't need to fully check it, but you do need to make sure you don't have log of 0, log of negative number when you plug that answer back in. So for example, I got log base 3 of x minus 1 is equal to 4. Step 1, get everything with a log on one side, numbers on the other. Well, all of our log expressions over here and our constant terms over here, so that's done. Step 2, use properties of logs to get a single log. Well, we got a single log, so that's done. Step 3, use the definition of log to rewrite an exponent form. Remember, this number that follows your log is your b, and then what follows that is your q, and then the other side of the equal is your p. Our exponential form is b to the p is equal to q. So b is 3, p is 4, and q is x minus 1. And then step 4 is we want to solve for x. 3 to the 4th is 81. equals x minus 1. Take negative 1 over, we got 81 plus 1 is equal to x, or x equal to 82. Maybe. Like I said, we do need to check to make sure that does not cause us to have log of 0 or log of negative number. If I put 82 back up here, 82 minus 1 is 81. That's not 0, it's not negative. So that'd be our answer. Although I'm not going to finish this problem, because it won't actually work out. I'll show the setup. Okay, step 1. Get everything with a log on one side, numbers on the other side. That's done. Step 2. Use properties logs to get a single log. Here we have log of something plus log of something. Remember, addition becomes multiplication. So this is log of x minus 5 times x plus 1 equals 5. When I FOIL that, I get x squared minus 4x minus 5. Then you use your B and P and Q. This is your B, this is your Q, and this is your P. Step 3, you rewrite this in exponential form. So B to the P is equal to Q. So I have 2 to the 5th is equal to x squared minus 4x minus 5. And then you solve it. This would require the quadratic formula, since I made problem up and it's not going to come up nice. I suspect everyone you'll run across in the homework will be nice. Will factor nice, so you have x minus 4 times x plus 3 type of setup. And that's all I really wanted to cover there. So let me go ahead and stop recording and answer any questions you have.